Yes, today I will be talking about the modern C++. I know it's not the newest of the C++ standard. The newer one would be C++ 20, and next year C++ 23 will be hitting. But we are aware that especially in HPC, the compilers lack the support or lacked the support previously. And so it's very understandable to switch to C++ 11, 14, or 17 now and not 10 years earlier. Today, first there will be a brief introduction, then I will just go through the, at least to me, most important parts of the changes of C++ 11, 14, and 17. The most important slide for you is probably this one. What are my definitions? Well, everything before C++ 2003 I call old C++. You might as well also call it good old C++. Everything after C++ 11 and before C++ 20 I call modern C++. And the newer standard, so C++ 20 and beyond, I call next C++, but I don't speak about them pretty much at all. So they are not on the slides. I might mention them sometimes, but the focus of this talk is primarily on C++ 11 to 17. I've looked at the compiler support of the general compilers, so GCC Clang and the Microsoft Visual Compiler, and almost all of them support C++ 14 and 17. And in terms of C++ 20, only Microsoft compiler supports everything, and GCC is very close. Now, this is for the general compilers. In the case of a cluster, there might be special ones. You need to check if they support everything. I would hope so, because C++ 11, I mean, that's 11 years ago. But please check before you start making changes to your code base. My own problem was I am too young to remember the good old C++. So I really needed to go through the books to find out, well, what is the difference? Because I was taught C++ 11 from the get-go. And so I would be very happy about any feedback regarding this talk, if it helped you or not. I have roughly 45 minutes. I hope I will not talk more longer than that. And since there are only 45 minutes, I won't be able to talk about everything, and I won't be talk to you about everything in detail. So this is just a subset of things I won't talk about, which is also kind of important, but not the big features, not the big changes. References which I've used, I've basically used two different approaches. The one was I looked at the books which introduced the differences, like an update, like a diff of the C++ standard, which is my favorite, Effective Modern C++ by Scott Myers and C++ 17 by Peter Pohmann. And in general, I'm just looking at the webpage CPP reference. This is a great resource to look everything up. They have nice descriptions, they have good examples. So that's where I look for stuff. Now, I already told you 45 minutes is not enough to talk about everything. There are lectures at the FAU about C++. At our chair, there are advanced programming techniques, which basically goes through the whole standard and tries to teach you everything about C++. There is also the smaller online class, Advanced C++ Programming. Outside of the university, there are some YouTube channels I like very much. The first one is C++ Weekly with Jason Turner. Every Monday, there is some topic he talks about. Another YouTube channel is Copper Spice. They have a set of videos on modern C++. They are very informative and not that long, so you can go through it bit by bit. And on the recent, I think 3 or 4 CPP cons, they've always the back to basics tracks where experienced people have a talk about, for example, smart pointers, for example, the special member functions of a class. So basic stuff you should, a modern C++ programmer should know, at least in theory. But from time to time, I rewatch them again, because from time to time, I tend to forget some things since I don't use everything. Regarding programming languages, the best way how to learn is exercise, of course. I've picked 3 websites which I use not only for C++, but also for other languages when I want to try a particular language. There is accessism.org and codinggame.com, which are basically 2 websites where they give you a task and you have to implement it so you can pass all the tests of the task at hand. I particularly like accessism.org because after you successfully finish the task, you can look at the solution of other people, and with that you almost always learn something new. So the C++ track, I've done that myself, like the first 20 exercises or something like in this range, and really the exercises were very well structured. They taught me something new, especially about the standard library. The coding game is a website where it's a little bit more flashy, so usually there's some kind of game you basically create a bot for. And last but not least, every December there is the Advent of Code, which means there are basically 2 tasks every day of December till the 25th of December, and you can solve it in any language. You can get just a string, an input, and you're expected to produce an output. And it's also a great way to practice programming. And since it's very popular and famous on the internet, there is really easy to find GitHub repositories full of different implementations in various languages. So let's get to C++ 11. I wanted to start with something really simple. And I also wanted to show you how this is going to work, and also mention what I'm not going to show you at all. In the old C++, we had Enum. This worked, but there are 2 big problems with it. First, it pollutes the namespace. As you can see here, I can use this red identifier anywhere, which also means it is everywhere in my namespace. And the second big problem with it was implicitly converted to and from integers, which is a greater resource of bugs, because you don't expect it every time to turn into an integer. The modern C++ offers you an enum class, and it has few special things. First of all, as you can see here in the switch statement, the enum has basically its own namespace where the identifiers are then specified. Secondly, you can give a type to your enum class, which means you can finally define how many bytes the enum is going to take, because it was actually not specified in the previous standard. And if you want to use your enum as an integer, you need to cast it by hand. So implicit casting doesn't work anymore. Why I have chosen this as an example, because here I can clearly show you that I won't mention every detail. Modern C++ also introduced opaque enum, which is like a forward declaration of this enum class. Also, unscoped enums can have a type, and I can use using a enum declaration. So there's more to it, which I won't be mentioned. And once again, I'm telling you this because I won't be covering every details there. This is just an introduction. That's why also I referenced the books in the beginning. So yeah, so you can study for yourself further on. Next topic I wanted to mention are the initializer lists. So in the old C++, if I wanted to initialize a vector with a set of in this case numbers, I needed to push back each and every number. And the initializer lists are the answer to that. Basically, it's a list with starts and ends with a curly bracket. And this bracket is transformed into an object from the standard library, that's standard initializer list, which is then passed to a vector. It calls the vector constructor, which gets this standard initializer list, and then the vector is responsible for handling it. This is nice in particular for maps, where you can create pairs, and from the pairs lists of keys and values, and you can very easily have, for example, constant variables, constant maps, to instead of a complicated if else or switch case statement.
Can I ask a question about this? If you could go back. Yes, so at which point is a mistake I made in terms of data types spotted by the, if you could go to slide 11, please. So for example, if I want to initialize a vector of ints, but one of the data types, not an int, obviously cannot be converted to int. So is that sort of spotted when the initializer list is constructed, or is it spotted when the vector is constructed?
That should be spotted. Initializer list is basically like a regular list. So it's need to have objects only of the type integer. So it has to be spotted during compile time, during the creation of the initializer list itself.
Okay, it's an int. Okay, sorry, yes, should have seen that. Thanks.
Together with the initializer list, there is this uniform initialization syntax. From the beginning, I thought it was a little bit silly to introduce a new syntax, curly brackets everywhere, when I want to create things. So these are a few examples. I can now create an integer with curly brackets. I can create a string with curly brackets. I can create a struct with curly brackets. It really depends on your coding style. For me, simple types like integers, I usually like to use the simple equals operator. For things like standard vector, if I have a set of fixed numbers, I would like this version. For my own classes, I tend to use the third version. And the nice benefit, which I observed while using the curly brackets, was I can immediately see when I'm creating new resources. Right? For integer, it doesn't matter that much, but for bigger resources, which consume memory, this is a great indicator that you are allocating stuff. The big reason why it was introduced, or one more benefit of it, is that if I would use the usual brackets as before, from the syntax point of view, you can't tell always if it's a call to a function or a call to a constructor, which is also a function, but whether it's a call to a function or a creation of an object. And the curly brackets will tell you definitely that this is a new object being created. And as you can see, funnily enough, if I am using the curly braces here, the syntax highlighter doesn't do its job and highlights there as a function. The problem now is that there are curly brackets everywhere. The only problem with this is when you combine aggregate objects and objects which expect an initializer list. So in this example, I have a struct which has two constructors, one of which is a regular constructor with two values, and one of which is an initializer list. And per default, it calls the initializer list function because it's the one preferred. So you shouldn't mix those up. If you have a struct which has multiple member variables and you want to define constructors for that, you shouldn't mix it up with initializer lists. So this was easy so far. The next big thing is auto. I'm sure some of you heard about it, and some developers don't like it very much. What is it? In the old C++, I needed to define the types by hand everywhere. So in case of, if I wanted to save an integer in a variable, I needed to define that it's an integer. If I wanted to save an iterator from a vector, I would need to type it out. And sometimes these types are really complicated. So I found this nice example. I didn't fill it out because it was just way too long, and it needed some special template functions to figure out the type of the value of the iterator being put into a function. On the other hand, in the modern C++, auto does that for you, so it deduces the type. This comes especially in handy with complicated types like the iterator of a container, and also types which are really hard to figure out by hand. Why don't people, especially the old C++ guys, don't like auto? Because sometimes it's used wrongly. If I have a function which is not templated at all, and for example, it gets 3 numbers and returns an integer as well, I might use auto, but I shouldn't, because types of the function are part of the documentation itself. And here I should have specified integer because it will be always an integer. Similarly, if you have a templated function, just use the template again if nothing is in your way. So this is the easiest thing how to make people mad if they need to use your API. Just use auto everywhere, then nobody will use your code. You can also use auto for instead of implicit casting. So in this example, I have a function foo, which returns a double. And the old dirty way would be to copy this output of the function into a float. With this, I have an implicit conversion. Later on, if the function gets changed somewhere, maybe my code will break, or the implicit conversion doesn't work anymore, or doesn't work as intended. With modern C++, I should always define my casting. Cast itself shouldn't be explicit. And with the explicit type initialization idiom, I can use the static cast to define that it should be a float. And then, since I don't want to repeat myself, I just set the variable to auto. There is the pendant to auto. It's called decal type. And with decal type, I can figure type of a thing. So in this example, there is a vector, and I wanted to have the size of this. However, the vector size is some size type defined by the standard library. The easiest way would be to write auto. If you don't want to use auto for some reason, for some more advanced example, you could use decal type to figure out the type this way. So now that we know how to use auto, we can use it in loops as well. So earlier we could just iterate over the vector. We have two different possibilities. We can either iterate over the from 0 to till the size of the vector, or we can iterate over the iterators of the vector. Both of which you need to type a lot of types in order to get what you want. With auto, this is all handled for you. The compiler just deduces the type for you, and it works just as expected. Now, these for loops already look really, really nice. However, we can do even better. C++ 11 introduced range-based for loops. The syntax looks like this. I have some kind of variable which will be iterated over. In this case, a v, and in this set of slides, v is always a vector. And there are different types of the variable which I then will use inside the for statement. In the first example, there's this auto I, which basically creates a copy of every of every element in vector, and I can use that. If I want to access every element of the vector, I just use a reference. If I want to save the copy, I just use a constant reference. And also, I don't need to use auto every time. I might as well use the regular types. And one thing I didn't mention, you could also use a structured bind, for example, for maps. So it will unpack the map. And in the first and second values here, we will have the key and the value of the map. Now we'll come to lambdas. Lambdas are a huge part of pretty much every language nowadays, because it is very easy to work with them. However, I know that especially if you spend your past 20 years in imperative programming, they are harder to grasp than other features because this is a whole new paradigm. Basically, it's functional programming, and lambdas are just not named functions. So what is functional programming? In functional programming, the functions are first-class citizens, meaning that they can be bound to names, pass as arguments, and even return from other functions. A function object is something which you can call. Usually they are also called functors or callables, depending on the language. In the standard, it's defined as a function object. But if you're coming from Haskell or other functional languages, they usually call them functors. In C++, the examples are functions or templated functions, class with an overloaded call operator, the previously mentioned lambda, or member function. So anything I can call as a function object. Why do I need lambdas? What can I use lambdas for? I mentioned lambda is a non-named function. I will show you in a minute. And what are they used for? Well, the examples I wanted to show you, I wanted to make them simple enough so you can immediately understand what the benefit of a lambda function is. So I can create a predicate for sorting. I can quickly create callback functions. I can use them as function objects for various algorithms in standard lib. And also I can use them for multi-threading. This is what a lambda looks like. There can be more to it. The syntax could be a little bit more complicated, especially with C++ 20 and 23, where concepts are introduced. But this is what a basic lambda looks like. We have a capture list. I will explain them in a minute. We have, like in a regular function, a set of parameters. We might specify a return type. And then we have the function body. Usually,
Jan, there's a raised hand by Jan Eitzinger.
Very short question. So this lambda, how is this related to a closure? So in other languages, you have this notion of a closure, which kind of captures, or you can reuse. You can use the environment, and it has the environment available in the lambda.
I will mention that in a minute. I wanted to skip captures first, so you see the simple lambdas first, and then I may mention the captures. So it's I will return to that question. Now, usually lambdas are locally used functions, and since they're only used locally, it's perfectly fine to use auto, and that's what you will see most of the time. So this is some kind of basically an identity function where it just returns what it receives. That's pretty much how lambdas look like. this is the simplest example. It came to my mind where you can see a usage of lambda. It's basically a callback. So you could either do, for example, if you want to iterate over every element of a vector and you want to increase every element, you could do this with for loops, or you can do it with a algorithm from standard library called for each, which pretty much does the same from beginning to the end. I will apply to every element this function.
Question to the upper example. Do you need the and sign only? I thought the and sign only if you want to change E and V.
Yeah, but yeah, sure. So the question
based on your slides.
Do I need the and side?
Yeah.
If the and side wasn't there, then this operation would be pretty much meaningless. I'm increasing the value, which then gets out of scope.
True. Yeah, but yeah.
Without the ampersand, each E would be a copy of the element of V.
Right. So if I have a vector, if I would have a vector of 1, 2, and 3 with the ampersand, the outcome, the V will contain 2, 3, and 4. If the ampersand wouldn't be there, then V would remain 1, 2, 3. So if I'm copying the element, so the ampersand isn't there, I'm not modifying V. That's pretty much it.
Okay, so the and sign has a separate meaning, not only dereferencing in that case. Because otherwise E would be a pointer if you dereference E here, and then you increase a pointer and not some value. Okay, I don't get C++, I see that. Okay.
The ampersand, yeah, I know what you're confused. No, this is not a pointer, it's a reference. That's a, I will mention references, but references were in C++ 98 already. You can imagine it as a pointer, which is always dereferenced. It's a little bit wrong imagination, but you could imagine it that.
Okay, yeah. yeah, I'm happy. Yeah, totally.
And if the ampersand isn't there, then you just have a value, and that thus V won't be changed at all. I will get to references at the end of the talk. Anyway, here are a set of more meaningful examples, because here even I'm not sure which example I would like more. It really depends on your code base. It really depends on whom you are working with and what the code should be looking like. I'm sure many of you will say this is nonsense, this for each. This is way clearer. Yes, because I'm used to it. I'm not saying it's wrong. I'm just trying to get the perspective here that you can use, in this case, you could basically use both. My answer would be, I mean, this is a really simple case, but my answer would be the less lines of code I have, and this is a simple line of code, the less errors I have. But in this case, you could do fine with both. Now there are some more meaningful examples. In the standard algorithm, there's a function which returns true if some kind of predicate is true for every element of a container. So in this example, the all-of function will iterate through the vector. It will apply the function and make a big and around everything. In this case, it's simple. I'm just testing if all the values in V are larger than 0. So this function will return true, and only if all the values of V are greater than 0. If one of them is less than 0, then it will return false. With a for loop, you would need 4 or 5 lines of code. You would need a Boolean variable. You need the for loop. You need to check. You need the if condition, and you need to save or break out of the loop and set the variable accordingly at the end.
A question about the first example. How does the compiler infer the type of I if I write auto in this case?
The auto here basically works like a template.
Yes, okay.
there will be detailed example, like 2 slides in the 2
Okay,
slides.
thanks.
Another example will be standard sort. In this case, I still iterate over a vector, but in this case, my vector consists of some more complicated class. Imagine any class, for example, standard pair, standard tuple, or your own class. I could have used auto here as well. I just wanted to make sure that you understand this is not an integer. And I can, like that, I can quickly, for a certain purpose, write my own predicate for comparing 2 objects of the same class. So for example, if this would be a vector of standard pairs, and I want to sort the pairs only by their first value, this is how I would do it. 1 line of code, really simple, everything is in its place, and everybody or your cell, which comes afterwards, will be able to see what's going on in 1 line of code. Last but not least, I could use also a function from standard lib in the numerics header. In this case, it's an accumulate function. Usually accumulate is used for summations, but I can use it for multiplication as well. If I wanted to multiply, so create a product of every item in the vector, I again iterate over the vector, I pass the initial value, and then I pass a function. And in this case, I can also use the function in the functional header as well. This is basically a lambda, where it adds up 2 parameters. That's it. I included this example so you can see that the functional style is getting more and more into C++ because it's really, once you get into it, it's really easy to understand. So I promised captures. Here are the captures. I tried to produce a really simple example. In this case, I just wanted to do the accumulate, so a summation over a vector, but not with accumulate, for the sake of this example. So I need some kind of variable where I want to sum into. And then I use my for each function, I iterate through the whole vector. And then I capture the n. There are 2 different possibilities how to capture things. I can capture by reference and I can capture by value. In this case, I want to capture by reference, obviously, because I want to change the n. And then I just add up the element at hand to the n, and since it's a reference to the n right here is going to be changed. Now, in other languages, lambdas are called closures. That was the question from, I believe, Jan previously. It's the same with function objects, functors, callables. It really depends where you're coming from. In C++, it's just a lambda, and it's a lambda with a capture. That's it. But sure, programmers, if they mean lambda and it's capturing stuff, they tend to say closure. It's not technically right, but everybody says that. So in this case, I'm creating a closure, I'm capturing an variable, in this case the n, and the n is then available as a reference inside my lambda function. Since Georg asked how it looks like, you can use a website, CPP Insights, to roll out the functionality of a lambda. So I stay with my example. I have a variable n, and I have a lambda which takes the n as reference. It captures the n by reference, and it sums the given parameter on the n, and that's roughly what the compiler will produce for you. So it basically creates a class, a callable object, a function object to be correct. The class will have an overload operator, call operator. Since it's an auto, right? We specified an auto, and I promised you auto works like templates, and it really is a template. In this case, auto gets rolled out to be a template. I remains same name I. So we have our template member function. And in this member function, we are then firstly casting n to whatever the element's gonna be. And then we cast back again into n. So the compiler makes sure that your code works properly with all kinds of inputs.
So this means the ampersand in the case of a capture is reinterpreted not as an address operator, but more like an addition to a type, like a reference type. It's just that the actual type is missing because it can infer it from.
That's what confuses you. Right. This ampersand, this ampersand right here, usually if there would be an ampersand in a code, this would mean an address of operator, which would return you a pointer. Now, in this case, it's like a reference to n. You are not getting a pointer, you are getting an alias. And
I think I would have written something like auto ampersand n. This would probably, I don't know if this would work, but this
won't work, but this basically, you've understood correctly. That's what it basically does. Yes.
That's what it does. Exactly. Yeah. Thanks.
I mean, you don't need the auto because if you would write the auto, you would create a new variable, but you are just pushing the reference in there. If you look at the class again, this is basically the constructor. The constructor, which is immediately called during the lambda, namely because we are referencing the n. It receives a reference to some variable and it stores the variable inside a reference n. So on the inside, it's really just a reference. And this is also the big problem with closures in C++, because C++ always offers you a new ways how to shoot yourselves in the leg. Now, what will happen?
Raise hand by Fabian.
Yeah, there's a question.
What is the auto I for?
The auto I is just a parameter. So in this case, I could also write the integer I, since I will be using, for example, integer. The auto I just tells the compiler to handle it as a template. That's this member overloaded call operator of this generated class.
Because you don't use the I, therefore I ask.
Yeah, in this case, my code just ends. If you remember the previous version, this function was then just put into another function, which is used afterwards.
Okay.
So I needed the code to look like this. So the lambda function is stored somewhere. In this case, I called it just f. So I can store the lambda functions like regular objects. Remember, functional programming functions are first-class citizens, so they behave pretty much like objects. And I mean, it's generated like a class and therefore like an object afterwards. And that's also what you see here at the end of the line, end of the slide. The lambda is then created. Remember the uniform initialization syntax. It passes the n. That's the n from the outside. It goes into the constructor. It gets saved as a reference, as a member variable. And the whole thing, the object, is stored in a regular variable f of this weird class. That's all the magic there is. Basically, lambdas are just a fancy way how to write yourself a class which is callable. And if you are using captchas, which creates you a more interesting constructor and which saves some private members.
So again, so when you go back one slide, please. So you say the I makes sense because you had the F defined the page before. This is why you need the I, or do you even do not need the I in this example?
Yeah, in this example, I wouldn't even need the I. So yeah, sorry. In this case, I've written one. This could be.
Okay, that's the point.
Sorry about that.
Okay, now I understand.
It's probably a typo.
Okay.
Yes, stupid example. Sorry about that. Compiler should me give a warning that I'm having a parameter which I'm not using. Sorry, this should be a y I.
Okay.
Maybe a very short additional question. Maybe I didn't get this auto thing. I mean, in Golang, you have this colon equal sign to also automatically determine the type of the left-hand side. But still, the left-hand side at compile time has a deterministic type. In this case, as you said now, this is not the case here, but this is an automatic, this is an arbitrary type depending on who is calling this thing, or is it like that? So could I put auto in the argument list of a function, and then it will take the type with whatever this thing is called?
No, well,
I don't get what the auto means. I have to be honest, because I mean, when I put the auto before something that's on the left-hand side of an assignment, okay, that's clear, yeah, because then the type is on the same line. You can determine it from the expression. But when you put it like in a function prototype, things are more complicated, yeah?
So essentially what you do with the auto is that you declare a template. It's similar to a template. You could do like template T and then Ti. So
Okay.
whenever you actually call that lambda, you instantiate this template for this particular type.
So it's an automatic template where you don't explicitly write out the template. But isn't this terribly failure?
Why?
Fehleranfällig?
Why though? What would be the failure?
Well,
that you introduce types and you don't know in your code while you're reading it what is going on there because you don't know the type.
Yeah,
I mean,
exactly,
is it C++ still? Does it still apply implicit type conversion?
Yes, of course.
Dude,
yeah,
that's exactly nightmare.
That's exactly why I mentioned that some people don't like auto at all. It's exactly this case. Well, with lambdas, usually you write lambdas and you use them right away, or you pass them right away. So from the context, you see what type you have. If you don't like the auto, you could also write int here. Perfectly possible.
Isn't it more like a function pointer or function reference in this case? Because on the right, I have a lambda.
Yeah. In the end, as you see here, it creates an object. It's just a plain old class with a call operator. So it's just an object to a class, and I can then call it like every other class which has an operator, a call operator overloaded. And yes, this is what the function objects, functors, callables, these are all the examples. Function pointer, functions, lambdas, objects which are overloaded with the call operator. At the end, it's the same thing because I can call them all. Is everybody now properly confused, or do I need to explain something about lambdas again?
Could you go to the next slide again, please? When you have where you had the auto F.
This one?
No, the previous one. Yes, this one. This one. No, I think 27.
Ah, yeah, thank you.
So in this case, what's the value of F?
You don't know. That's why you need to use an auto. I mean, if I roll it out through this CPP inside, the value of F would be this generated class. The class is generated by the compiler. So the programmer cannot know. That's why you use the auto here.
Okay, so that's what I meant by this is basically like a function pointer or function reference. In C, I would have written a function. I would have taken its address, and then later I can use the address of that function by dereferencing it and calling the function. Here, I'm like defining the function in line. F is a function object, and I can later call it.
Exactly. That's what I meant with functors, function object, and callables. All the same things I can collect later. The difference between a C pointer to a function and a lambda is that lambda has captures, and I can define it everywhere quickly and namelessly.
Okay.
Remember the examples here. In C, if I would want to use it somehow, okay, I don't have a container in C, but if I wanted to use function pointers, I would need to define the function somewhere and then use the name with the name % to get the pointer. So you are introducing to your API or a new function, which is really short, which, yeah, won't be used anywhere else. That's why you want a lambda, so it's inline in the code and not somewhere else.
Okay.
But at the end of the day, if you ignore captures, if you understand that the auto here is like a template, then it's almost like a function pointer. With C, you can pretty much come, you can come closer than that with C. Okay, after this lambda discussion, can we move on to the next topic, or are there any more questions? All right. So the lambdas were a little bit confusing. Now comes value categories and move semantics. This is lambdas and move semantics are basically the two big things which came with C++. If you understand those, you pretty much understand the most part of C++ 11. Every expression in C++ has a type and a value category. Types are simple. We had types so far. Yes, sometimes they're a little bit confusing with templates and orders, but every expression has a type. It also has a value category. There are 3 of them. There is the PR value, X value, and L value. And now I'll show you what they mean. So the simplest one is the L value category. This is anything which has an address or a name, for example, a variable or a function. It can be a string literal, an indirection, the result of an indirection operator, assignments, subscript expressions. Those are L values. So, for example, a variable X is an L value. An assignment A equals to B is an L value. The pre-increment of a variable is an L value. Therefore, dereferencing a pointer produces an L value. So those are the things which are basically on the left-hand side of an assignment. Now comes the X values. The X value is basically an L value which is about to expire. This is the last case I wrote in the list. It can be also a temporary object. Anything which is about to be destroyed, anything which is about to leave the scope, anything which is about to expire. The best example for here is standard move. So standard move doesn't move anything. It makes an L value and X value. So X is just some variable, right? It might be integer X. I want to change its value category, not its type, its value category. So I apply standard move to X, and then it's going to be an X value. The third category are PR values, which are basically literals, product of overloaded operators, basically anything which should be on the right-hand side of an assignment. It can't be on the left-hand side of an operand of assignment. It's something you can't take the address of. Examples, as I said, literals, the post increment, or for example, also a lambda function. Why is it important? Because previously in C++ 98, in the old C++, you had references, and those were always L value references. We had them before. Here I have just some variable I, which is initialized with 0, and I can create an alias, a reference, which is basically the same thing. Yes, you can think about it as a pointer, but it's not defined as a pointer. It's defined as an alias to, in this case, I. R-value reference is nothing else than a reference to a PR or X value. Right? In this case, we create a string. That's an object which is about to be expired, a temporary object. We cannot put it into an L value. This should be an ampersand. We cannot put it in an L value reference. We have to put it in an R value reference. So far, so simple. Every expression has a type and a value category. Types, you know that. Value categories are R value or R value, L value or R value. R values are things about to be expired, temporary objects, things that can be only on the right-hand side. L values are things with a name, with an address, things which will be on the left-hand side or which can be on the left-hand side of an assignment. Why is this important? Well, in C++ 98, we had copies, but we couldn't move objects. In the following examples, I will always use a vector class, my own vector class. It will have a data pointer to some data and a size. This is the constructor which looks like this. I give a certain size and it will store the size and also allocate the necessary memory. It's not a standard vector, it's just a plain, simple class holding the data and the size. Now, previously, you could use copy constructors, or you are using copy constructors. That didn't change. Copy constructors are basically a constant R value reference, L value reference. So you can use the object, but you can't modify it. And you need to copy out the data. So in this case, I'm starting from the begin to the end of the other vector, and I'm copying it into the data. That's plain old C++. Now, move constructors use this R-value reference. So it's a constructor for something which is about to be expired, which is about to be destroyed. And the idea is this: I can steal its resources. So I have two vectors. One is about to be expired, and I'm constructing a new one given the old one. I just copy the data, I copy the size, and then I set the other data to nothing, to null pointer. I've stolen the memory allocated in the other vector, and I gave nothing back. So there is no copy involved. This is just two pointers being exchanged.
Could that be called a shallow copy with usable semantics?
No, because in shallow copy, you then have two objects which point to the same thing. Here I'm making sure that the other object points to nowhere.
That's what I mean by usable semantics. So I destroy the source, so to speak.
Yes, exactly. You don't have to destroy the source, but you should. I've never seen valid code where you don't destroy the previous owner. And with the move semantics, well, you don't need to copy everything around, especially with big data structures. You can move them.
The destructor of the source object will still be called, right? But it doesn't matter because the data is a null pointer. Exactly.
So, I mean, since it's an R-value reference, so it's a thing which is about to be expired. So in the next few steps, its destructor will be called. And I need to make sure that its distraction will be still valid. So that's why I'm setting the size to 0 and I'm setting the data to null pointer. So I can then free the data. If I free to null pointer, nothing happens.
Okay, thanks.
And with this move operation, I basically don't have to copy. That's the saving I'm doing. A colleague of mine, whom I introduced to this effective modern C++ book, complains to me all the time, all this so I can sometimes move instead of copying. Yes, basically that's it. There's a little bit more. There are also move assignments, of course. I mean, if you have copy constructors and copy assignments, you will have move constructors and move assignments as well. But there is also then other things you need to think of. First of all, there's rule of 5. Previously, it was known as rule of 3, but now since the move operations are there, it's 5 functions. Those are the special member functions of a class. There are rules how and when they are generated. So if you want to use them and you don't need to implement your own copy or move assignments or destructor, then you don't need to worry about it. However, in my case, in this vector case, I have a variable. If I don't copy by myself, if I don't move by myself, I will have a shallow copy. I will share resources, which is not the point. And the rule of 3 was, if I have a copy constructor, copy assignment, or destructor, I need to implement the other ones as well. Rule of 5 is basically throw the move operations also in the mix. We'll look at that. We will look at that in a minute. Are there any questions regarding the move constructor and move operations in general? Now, the last thing I wanted to show you were the smart pointers, which is the new thing in standard library in C++11. In C++98, in the old C++, you had your old row pointer. Just a pointer points to somewhere. At the end, I need to delete it. I'm responsible for its deletion. The problems are sharing of pointers, shallow copies, stuff like this. And also deleting a pointer is not always easy, since it is very easy to leave a function unexpectedly or at some other point, and you would need to put the deletes everywhere at every return or other means of getting out of a function. So it's really hard not to shoot yourself in the leg. That's where the unique pointer comes in, and that's also why I needed to explain to you the move semantics. So unique pointer is a smart pointer. It's a new class in the standard library. And the whole point of unique pointer is it owns the resource it points to. And when this unique pointer leaves scope, then it will automatically destroy the pointer at hand, the pointer it holds. So in this example, I have a unique pointer of the type integer. It's called IP, like integer pointer. And I'm just creating a new integer on the heap with the value of 15. If I then leave the function, so I return, or I leave the block of a for loop, for example, when IP gets out of scope, the destructor will be called automatically. The feature of unique pointer is it cannot be copied. So its copy operations, that is copy constructor and copy assignments, are deleted. They are not available. You cannot use them. So if I have like previously, my unique pointer, I cannot simply copy it. This will produce an error that this doesn't compile. So nobody can steal my resource, and I own it. The only way how to put my unique pointer somewhere as a unique pointer is to move it. So I'm putting this unique pointer in standard move. The standard move does nothing else than says, hey, the thing which comes out is now an X value about to be expired, which means then when I'm creating this IP2, I am using not the copy but the move constructor here. And so the unique pointer itself then responsible stealing the resources of IP and set it to, for example, to null pointer. Right? IP is null pointer now. IP2 owns the resource. I cannot use IP anymore. That's it. Now I wanted to extend my vector, my little vector class a little bit, because we used the raw pointer previously. And if you want to use C++11 and go on, the recommendation is always to never use raw pointers. There are some exceptions, of course, to that rule, but general and especially in classes where the class holds a resource, smart pointers are the best way to go. So in this case, the only thing which changed is I put my data integer pointer and I made it a unique pointer. That's all that changed. Now, this is my default my constructor where given a size. The size parameter is missing. Sorry about that. Given a size, I just create my vector as before. I am using this standard make unique function to give me a unique pointer object, which is, since it's a return of a function which is about to be destroyed, is about to be expire, which is then initialized as this data unique pointer object. So I hold my data now in this unique pointer. The copy constructor looks like the following. Again, I have some other vector, and you can, I mean, in C++, there will be always a way how to shoot yourself in the leg, and this is also the exception when raw pointers are very necessary. The standard copy wants to have an iterator. In pointers, for example, you can iterate over that. You cannot iterate over a unique pointer. The unique pointer itself offers you a get function which gets you the raw pointer. It's like the telling the compiler, I know what I'm doing, give me the raw pointer. I promise I won't save it somewhere else. The unique pointer should still own it, but for especially functions like in standard algorithm, it's very helpful to have access to the underlying pointer. Other than that, it works completely as the same as the raw pointer. Since unique pointer implements the move semantics by itself, the move constructor is then very simple. I use the default keyword, that's a new keyword in C++11. I use just the default keywords, which says, please compiler, do as you would usually do, create a move constructor for me, because I know all my things can be moved and you can do it without problems. This is also the same for the destructor. Since when vector class, the vector object gets out of scope, the default constructor will just call the destructors of the individual objects, the members the class has, and unique pointer will then free the data automatically. So I don't need a special destructor anymore. And of course, you need to follow the rule of 5. So you need also a copy assignment and move assignment. Again, move assignment really simple. I just use the default one. Copy assignment, I need to implement by myself. There are two more pointers, two more smart pointers. The first one is the shared pointer. The shared pointer is your classical reference counter. It's a class which remembers how many instances are pointing to this resource. And once this reference goes to 0, it will then and only then free the resource. So in this simple example, because I think shared pointers are pretty easy to understand, I again have some shared pointer. I'm creating some resource, in this case, one integer. And unlike the unique pointer, I can copy the shared pointer. And during this copy, the reference code is increased by 1. So I have 2 of them now. I have 2 instances which point to the same thing. And at the end of the function, this pi2 gets deleted. So my reference count is only 1. And since I'm returning the PI, it basically gets copied out, so the reference remains 1. However, if the caller doesn't use PI at all, the reference counter gets to 0, and then the resource will be deallocated. So this is just a reference counter class, especially useful, well, if nobody particular owns a certain resource, you are sharing it. So that's when you use shared pointer. The third in the group is a weak pointer. Weak pointer is basically a pointer which knows what shared pointer it's using. It's a little bit confusing in the beginning, but we will get through it. It's a non-owning pointer. So you will have to do some special step in order to access the resource which it points to. At the beginning, you have a shared pointer. In this case, I'm using the make shared function. By the way, you should always use the make share functions and make unique functions. They are a little bit faster and also less error prone than writing the standard shared pointer here. So that's why I use this idiom with auto. SP is now my shared pointer. I then use the shared pointer in the constructor of a weak pointer. Since it's a constructor of a weak pointer, the shared pointer reference is not increased. It's still 1, just this one SP shared pointer value. However, the weak pointer now knows what part of a shared pointer it is. If I then use the weak pointer somewhere else in my code, there is a T too much, the T shouldn't be there. Oh, that's completely wrong. Oh no, wait, no, it's correct. No, it's wrong. I made a little mistake. This variable should be called VP, not GV. That's pretty much it. But anyway, somewhere else in your code, when you want to use this weak pointer, you're using the log function, which checks whether this shared pointer it was used to construct this weak pointer still exists. The resources are still greater than 0. And if it does exist, it creates you then a shared pointer, which then you can use. If it doesn't exist, then your weak pointer expired because the shared pointer was freed somewhere else. Why do we need these weak pointers? Imagine a simple structure. I have basically something like a graph. So I have objects, and somewhere it starts. Right? Somewhere I have a variable s, which is the start, and I'm creating graph like like so. The problem arises with the last link. Now, if all the arrows here, the straight lines, the undotted lines, are shared pointers, and this one will be shared pointer as well, then once I delete, I free, the s comes out of scope, the reference count remains 1 everywhere. This is a memory leak. Right, with the shared pointers, I create a memory leak if I create a structure which points to itself. The weak pointers are the solution for that. Namely, this guy should be the weak pointer. Because then when I delete the s right here, nobody points to this element anymore, so it gets destroyed. And while it gets destroyed, it will destroy its shared pointer. It's destroyed. Then this element is the next target because nobody points to it. So the shared pointer is get called, and so on and so forth. So I can remove then the whole collection of objects. But I can only do it if the last link here in this case is a weak pointer. If it isn't a weak pointer, then still somebody is pointing to this particular object. One other example would be, for example, a tree. Trees are where they come often in computer science. They are useful. So if we have a structure like so. But oftentimes, I would want to have also some kind of link back. What kind of pointers do I want to use? Well, I told you C++11, raw pointers are not the best solution. So what of the free smart pointers should I be using? In the downward direction, this should be a unique pointer, because usually the parent owns a child. On the upward direction, this should be probably a weak pointer. And the child then basically has to check whether the parent is still alive. And it's the only way how to assure that if I delete the initially the root of this whole tree, then everything gets deleted as well. With this type of unique pointers, not with shared pointers, but the principle is the same. If I would point back with something else than a weak pointer, with a smart pointer, with a shared pointer, then I would still have a reference to this object, and the tree again would produce basically a memory leak. Do you have any questions?
All right. Thank you, Jan, for this very interesting talk. Thanks again, and see you next month. Bye-bye.